morning. Now this is our third class on the module 2 rotational mechanics. Now today we are going to determine the moment of inertia of some solid bodies having regular shape like thin rod, circular ring, circular disc, annular disc, cylinder, sphere, etc. Okay, so the procedure that is followed in each of these processes is listed here. That is, first what we do is we obtain an expression for moment of inertia of a very small mass point or element of the body about the given axis. Okay, then we integrate it over the appropriate limits to cover the entire body. That is, now from today onwards we are going to determine the moment of inertia of various solid bodies like circular ring, circular disc, etc. So in each of these cases, first what we do is we find the moment of inertia of a very small element of the body given. Once that moment of inertia is calculated, we will integrate that over the appropriate limits to determine the moment of inertia of the whole body. Okay, that is the step that we are following in each of these cases. Now today we are going to find the moment of inertia of a thin rod. So here today the solid body that we are going to take is a thin rod. Now consider a uniform rod of mass m and length small letter l. We determine the moment of inertia of the rod about an axis passing through its center and perpendicular to its length, and also about an axis passing through one end and perpendicular to its length. So here you are going to find the moment of inertia of a thin rod of mass m and length l. Okay. Now first we are going to determine its moment of inertia about an axis passing through its center, okay, and perpendicular to its length. Okay, this is the figure. Now let z dash be the axis passing through the center O of the rod and perpendicular to its length as shown. See, z dash. It is an axis passing through the center of the rod O and perpendicular to the length L. Okay. Then consider an element of the rod having length dy at a distance y from O. See, you are considering a very small element of the rod and it's having a length dy. See, dy, and it is at a distance y from O. Everything that is described is clearly shown in the figure, so there is no much confusion. Okay, so as I said before, first we are going to consider a small element of the thin rod. We are going to find moment of inertia of that small element, and after that we integrate over the appropriate limits to get the moment of inertia of the whole body, here whole thin rod. Okay, now mass per unit length of the rod will be capital M by L, and that capital M by L, that is mass per unit length, is denoted by small letter m. So mass of the element dy that we have considered will be equal to m dy. Now moment of inertia of the element dy about z dash will be, what is moment of inertia? Mass into distance square, right? So this is a mass already you have, and the distance square, that is y square. Why? Because the small element that we are considering here, that is dy, is at a distance y from the center O, right? Okay, that is why y square. So this is the moment of inertia of the small element. Okay, now in order to get the moment of inertia of the whole thin body, what you have to do, as I said earlier, you have to integrate it over the limit minus L by 2 to plus L by 2c. Okay, that will give you capital I, that is moment of inertia of the whole thin rod. Now this minus L to plus L, or minus L by 2 to plus L by 2, here you are changing the limit from minus L by 2 to plus L by 2 to 0 to L by 2. If you change that limit, you have to multiply it with the 2. That is why a 2 is coming. That is simple mathematics, which you might have studied in your classes of integration. That is, if you have an integral like minus L to plus L y dy, if you are changing the limit from 0 to L y dy, you will multiply it with a 2. Same thing is done here. So this will become this. Okay. M is a constant mass per unit length, so it's taken outside. Now rest everything is integration. 2m. What is integral? Y square dy y cube by 3, right? Then apply the limit 0 to L by 2. So you will get this. And now how will you get this one? That is, you just replace this small letter m. What is that small letter m? Mass per unit length. So replace that small letter m with the capital M by L. So you will reach at this equation. Okay. Final answer is ml square by 12. That is the moment of inertia of the thin rod about an axis passing through its center and perpendicular to its length. That is the first case. Now second case, you are going to find the moment of inertia about an axis passing through one end. See, passing through one end and perpendicular to its length. The first case, you have found the moment of inertia of an axis passing through the center. Now you are going to find moment of inertia about an axis passing through one end and perpendicular to the length. Okay, for that consider this figure, and you have to draw this figure also. Okay. And let I dash be the moment of inertia of the rod about an axis passing through one end and perpendicular to its length. Okay. Here Z dash is the axis passing through the center. Okay. And moment of inertia about Z dash is represented by ICM. Okay, because it is a moment of inertia about center of mass. Okay. Now let I dash be the moment of inertia along the axis passing through one end. Okay, this one, that is I dash. Okay, so moment of inertia about an axis passing through center is Im, and moment of inertia about an axis passing through one end is I dash. Okay, so here you are going to apply the Parallax Theorem that you have already studied in our earlier classes. As per Parallax Theorem, what was the statement? I dash is equal to ICM plus MA square. Here ICM, we have already derived its expression, ml square by 12. What is it? ICM means moment of inertia about an axis passing through the center. Okay, that we have already found. This one, moment of inertia about an axis passing through the center, its expression ml square by 12. So you just substitute here, that is enough. Okay, ml square by 12 in place of ICM, you substitute ml square by 12. Here A is L by 2. That is the distance square. A is the distance between these two axes. That is distance between the axis passing through the center and the distance between the axis at one end. They are separated by distance L by 2. So that distance A is L by 2. So here in place of A you can substitute L by 2 square. See, substituting those values you will get the final answer as ml square by 3. So moment of inertia about an axis passing through the center is ml square by 12, and moment of inertia about an axis passing through one end is ml square by 3. This is the case of thin rod. Okay, so all these derivations are very important. You have to study it very well, understand the difference, draw the diagram, explain it very well and prove it. Okay, now today we will discuss one more solid body, that is a circular ring. Okay, same procedure. That is, first we are considering a small element. We find the moment of inertia of that small element, and after that you integrate it within the appropriate limits to get the moment of inertia of the whole body. Okay. Consider a circular ring of mass m and radius r. So here first we are going to find moment of inertia for about an axis passing through its center and perpendicular to its plane. Okay, see the figure. Let z dash be the axis passing through the center O and perpendicular to its plane. Well, it is very clear from this figure, right? Now you just consider a small element of the ring of mass small letter m. Okay. Now from the figure, moment of inertia of the element m about z dash is mr square. That is, moment of inertia is mass into distance square. Here distance is r. See this one. So mr square is the moment of inertia of the small element of the ring of mass m. Okay. Now since all such elements of the ring are at the same distance r from the z dash axis, the moment of inertia of the ring about z dash axis is given as sigma mr square. Okay, so this is very simple. See, first you find moment of you considered a very small element of the ring, say of mass m, and you found that that element is at a distance r. Okay, so its moment of inertia of that small element will be mr square. Now this circular disk is made up of many such small elements which are at a distance r from the axis. So in order to get the moment of inertia of the whole circular ring, what you have to do, you have to make the sum of all such small elements. That will be sigma mr square. Now what is sigma m? Capital M. So moment of inertia of the whole circular ring will be mr square. See. Okay. Now the second case, we are going to find moment of inertia about a diameter. For that, you just consider two mutually perpendicular diameters as shown in figure. Let that be xx dash and yy dash. Now let the moment of inertia of the ring about xx dash be ix, and let the moment of inertia of the ring about yy dash be iy. Now moment of inertia of the ring about the diameter, it will be the same. Okay, that is ix will be equal to iy is equal to id. Now you just apply the perpendicular axis theorem that we have applied. What was it? Iz equal to ix plus iy, right? Now here in this case, as we already said, since the moment of inertia of the ring about any diameter is the same, ix will be equal to iy, or so we can write it as ix is equal to id, iy is also equal to id. See, we have discussed about it. So iz can be 2id. See, but from equation 20 we have already discussed that iz, that is moment of inertia about the diameter about an axis passing through the center, is mr square. So you just substitute the value there. That is, in place of iz you substitute mr square. So mr square, this one, is equal to 2id. So moment of inertia of the ring about the diameter, that is id, will be equal to mr square by 2. See. Okay. So for today this is enough. So we have studied the case of a thin rod. We have derived the expression for the moment of inertia about an axis passing through the center, and also we have found the moment of inertia about an axis passing through one end. Now in the case of circular ring problem, we have found moment of inertia about an axis passing through the center, and also we have found the moment of inertia about a diameter. Okay, thank you.